In this question, we have a person of 55 kilograms jumping from a height of 2.8 meters onto the ground. So we have three parts. This question is relatively long, but let's see the first part. The first part asks us to find the impulse. And the impulse, as we know, is a change of momentum, which when his mass is constant at 55 kilograms, it's just mass times the change of velocity. So we need to find the velocity of this person. And this is done by using the conservation of energy, because we know he's falling from a height of 2.8 meters. So his initial energy, which is solely gravitational potential energy, will be equal to his final kinetic energy. That gives us V equals square root of 2gh. And when we plug in the gravitational acceleration and the height, we get a final velocity of 7.8 meters per second. So this is the velocity that he has when he lands on the ground. And the change of momentum is, if we just plug in the mass of him, times 7.4 meters per second, gives us around 4.10 kilogram meter per second. So this is his impulse. And impulse is always in the direction of the force. So in this case, the force exerted by the ground onto this person is going upward. So the impulse will also be upward. So now let's look at part B. Part B, we want to find the net force, the average net force of this person by the ground. And in order to find that, we have two ways of doing this. One way, which is the way we've been using throughout this chapter, is we know impulse equals F times delta T, which equals M times delta V. And M equals delta V, we already know what it is in part A. So then what we need to do is we need to find this delta T. This is one way of solving it. So how do we find the delta T? Because we know that in 1 centimeters of distance, this person decelerated from 7.4 meters per second to 0 meters per second. So from that, we will be able to find, using the kinematics, we will be able to find the acceleration of this person. And from the acceleration, we can try to work again to find the delta T. So with this, we have vt squared minus v squared equals 2ax. So this gives us A, and then from A, we'll be able to find delta T. This is one way of solving it, but there is another easier way that can actually omit this step. And in this other way, we only need to find A to find the force. And that is if we do not think in terms of momentum, if we think in our normal Newton's second law, we have F equals ma. And if we plug in this A here, then that would be the force that is used to stop this person. So in this case, we actually simplified this problem a little bit by not thinking in terms of momentum and impulse. So in this way, what we have is mg equals 55 kilogram times A. What is A? A is vt squared, which vt squared minus, which is also just 7.4 meters per second, times 2 times 0.01 meter. So that is the force that is required to stop this person. But other than that, when you look at this person, he also has this gravitational force acting on him. So we also need an extra force to support him against gravity. So this actually should be plus g. And now if we also add 9.8 meters per second squared, we get a total of 150,000 Newton. That's a huge force. And yeah, so that is a force that will be exerted onto this person by the ground. What about case C? In case this person lands again, but with a bent knee. So in this case, he can actually move 50 centimeters. So this number, 0.01 meter, will be replaced by 0.5 meter. So if we just do the same calculation again, plus 9.8 meter per second squared, we will have 4,000 Newton. Again, this is upward. And we can see that this is a lot smaller than this number. So 400 Newton is around like 4,000 Newton is around like 400 kilograms of stuff hitting you. So even though it's still a huge force, it's much better than 150,000 Newton. So when you jump, just for the sake of the house, try to bend your knees.